Good evening, all. I'm from Modgaval, T of this course. So I'm going to take a problem solving session on the fourth chapter, Interpretation of Batch Reactor Data. The course tutor is Professor Vishwana Mandals, Chemical Engineering Department, IIT Guwahati. I think all of you have gone through the weeks or lectures which are available on some portals. So this is a brief recap. Integral method of analysis of batch reactor data, part 2, then differential method of analysis and variable volume batch reactor data. Here is a performance equation for variable volume of batch reactor data. For first order, zero order, second, first order, second order, third order, and nth order. For plug flow and mixed flow. So starting from the MCQ1, the question A gives B is conducted in a isothermal batch reactor. If the conversion of A increase linearly with holding time, then the order of reaction. So here we mention that conversion of A is linearly with the holding times. So means conversion is directly proportional to the time. Correct. Then I have to calculate order of the reaction is. So we can start from the zero order reactions. The rate equation for the zero order reaction are equal to K C A, right, equal to TCA by dt. Right. Integrate these terms, so you will get CA naught equal to CA is equal to K T. Right. So as you C is equal to C, we can write down C is equal to CA naught 1 minus A. Right. So C is 0, C0 1 minus XA equal to KT. Right. So it XA is equal to KT is A. Right. So here the conversion is directly proportional to the time. It's a zero order reaction. So you can check for the other order of reaction, like for example, take first order reactions. Kt equal to ln x for first order reaction, n is equal to 1 by 1 minus x. Right. So Kt by xa. Right. So Kt equal to 1 by xa. By xa is equal to 1 by Kt. Right. There is a no linear in the for the first order reaction. Similarly, you can calculate. You can calculate about other order reaction, but here is a max zero order reaction. Yes. Question number 2. A conversion for the second order irreversible reaction constant value A gives B in a batch mode is given by. Okay. They have to calculate the convergence of the second order reactions. So the rate equation for the second order reaction dCA by dt equal to K2Ca square, right? Now take this concentration term Ca square equal to K dt. Now integrate Ca and 0 to t. So we will get Ca 1 by Ca now is equal to K2 t. Right. So Ca naught Ca equal to Ca to Ca0 equal to t. Right. As we know, C is equal to C naught 1 by x. E C naught minus C A naught into x plus C A x equal to C A naught minus C A. So put this in these equations. So C A naught x A equal to C A into C A naught. C A naught get cancels equal to C 2, right. So x A equal to C 2 C A and C, right. So in check option, region not a CA, so convert into CA not C2 or X into T. Right. So 1 by C2 CA naught to T equal to 1 plus XA, right. C2 CA naught equal to 1 by XA plus 1, right. So XA is equal to CA naught K2 T divided by 1 plus CA naught K2 50, right. Now check the options here. A, A2 C not option B is no. So yes, moving to the question number 3. A zero order liquid phase reaction A gives B is being carried out in a batch reactor with K equal to 10 raised to the minus 3 mole per liter per minute. If starting concentration of A is zero point 0.1 moles per liter, so the time in minute taken by the system before A is exhausted in a 100 liters reactors. So in these questions, initial concentration given means zero order reaction, and reaction is A gives B in a batch reactors. K give a, so after conversions, so her month total conversions how much time required, so that we have to calculate, right. So zero order liquid phase reaction, So the rate equation C A naught after integrating you will get C is equal to Kt, right? So when Ca is exhausted, that is C A naught is equal to 0, right? But C is equal to 0. Then T is equal to T full, right? So T is equal to T full equal to C A naught by Q. Here C A naught given 0.1 and K given 10 to the power minus 3 is right. Moving to the question number 4, for an isothermal second order aqueous phase reaction A gives B, the ratio of the time required for 90% conversion to time required for the 45% conversion is. So here the second order reaction isothermal means temperature constant. Reaction A gives B, the ratio of time required for 90% conversion to time required for 45%. So we have to calculate the ratio. For second order reaction, the rate equation uh, after integrating you will get say not equal to kt, right? Now here is a given convergence, so 1 by say not 1 minus xa by 1 by say not equal to kt, right? So you will get xa equal to 1 minus xa equal to k say not, right? Right? Now this is equation 1. Now, take a ratio by time required at 9%, 90% and 45%. So, K C A naught T 190, K C A naught T 45, right? So here, 0.9, 0.1, 0.45, 0.55, 11, right? The ratio of time required for 90% converted to time required 45 conversion is 11. Moving to the question number 5. The following rate concentration data are calculated from the experiment to find the activation energy temperature E by R for the first order reactions. So here are given say for different reactions, the rate equation with rate and temperatures. So we have to calculate the activation of this ratio E by R. For first order reactions, the rate equation RA equal to K C A, right? K equal to based on the redundancy law RT, right? So R equal to CA CA is equal to A naught is the E by RT. Right. So now for run 1 to 3. So by comparing run 1 and 3, R E C A 3 A naught E by RT by C A 1 A naught E RT 1. Right. So C A 3 C A 1 exponential E by RT 1 E by RT 2. Right. Now put the value which is given in tables. So 3 by 2 equal to 40 by 20 exponential 3 by 4 into 480 okay 480 minus E by R 500. Now ln 3 by 2 equal to E by take comma E by R, right? Then 1 480 minus 1 by 500, right? So E by R equal to 4865.6. So we can compare uh, run 1 and 2 and also 1 3 and 2 and 3. Now question number 6. A homogeneous reaction R gives P occurs in a batch reactor. The conversion of the reactant R is 67% after the 10 minutes and 80% after 20 minutes. The rate equation for this reaction. Okay, the conversion of the reactant R is 67% after the 10 minutes, 80% after the 20 minutes. Given time and conversion given. So I have to calculate the rate equations. So in this question, I have to calculate the order of reaction. So like 0, 1, 2, 3. Right. So here conversion given 67, then 10 minutes and 80% after 20 minutes. So I have to calculate the order of reaction. So So starting from the n is equal to 0 and rate equation here not are equal to k. Right. So k is equal to here not x r by t. Right. Now for t 10 minutes and x is 0.67. So k equal to here not into 0.67 divided by 10. Uh, 0.067 here not. Now check for 20 minutes. If k would be the same for 10 minutes, so it will be the zero order reaction. So first we check k is equal to cr naught into 0.80 divided by 20, 0.040 cr naught, right? So since k is not a constant, uh, so in that n is equal to, so this is not a zero order reaction. Now check for the uh, first order reactions, right? So k for first order reactions 1 by t ln 1 by 1 minus, right? So for t is equal to 10 and t is equal to 20. So here k will get 0.1108 and k is equal to 0.08047. This is not a first order reaction. Now check for the second order. For second order n is equal to 2. So k the rate equation kt c naught equal to k 1 by x or k 1 by k naught t into x 1 by x. Now for t is equal to 10 minute and x is equal to 0.60. So k is equal to 0.203 by c or not. Right. Our check for t is equal to 20 minutes and x is equal to right. So k is equal to 0.2 cr. So k is constant in are both the conditions. So hence given reaction is a second order reaction. Right. Now question number 7. An isothermal liquid phase zero order reaction A gives B with K is equal to 0.5 mole per meter cube is carried out in batch reactor. The initial concentration of A is 2 mole per meter cube. At 3 seconds from the start of the reaction, the concentration of A in a moles per meter cube. Right. So here we have to calculate the concentration after the reaction started within at a 3 seconds. Right. So these are zero order reactions. So the rate equation C is equal to C naught equal to Kt. Right. So C A equal to C naught Kt. Right. So here C naught given to K given 0.5 into 3 seconds. Wait, it's a 0.5 mole per meter cube. Question number 8. The liquid phase reaction gives products is governed by the kinetics. R is equal to K C A is to the 1 by 2. If the reaction undergoes 75 conversion of A in a 10 minutes in isothermal batch reactor, the time for a complete conversion is. So here T given and it's a given. So the time, so you have to calculate time required for the complete conversions. So here given these rate equations, right? Ra equal to minus dCA by dt equal to K C 1 by 2, right? Now take these terms here and integrate. Ca not Ca Ca by 2 is Ca equal to minus K 0 to, right? Ca plus Ca not Ca and Kt, right? Ca twice Ca 1 by 2 minus Ca not 1 by 2 equal to T. T, right? So since C is equal to C naught 1 by X, right? So put in this equation. So is CA naught 1 by 2 1 minus XA 1 by 2 minus CA 1 by 2 equal to KT. So is take a common C naught 1 by 2 1 minus XA 1 by 2 equal to minus KT. Yes, this is equation 1, right? Now XA equal to 0.75 and T is equal to 10 minutes. So put in this equation, so you will get CA naught 1 by 2 equal to 10 K. Right. Now for a complete conversion, X is equal to 1 and this is CA naught value given here. So put in the equation 1, so you will get T is equal to 20 minutes. Right. So for a complete conversion required the 20 minutes. Question number 9. An irreversible homogeneous reaction gives products has a rate equations R is equal to 2 Ca square plus 0.1 Ca divided by 1 plus 50 Ca, where Ca is a concentration of A. C is varies in the range of 0.5 to 50 mole per meter cube. or a very high concentration of E, the reaction order tends to. So for very high CA, here mention that the rate equations rate equal to twice CA square by 50 C, right, equal to 1 by 25 CA, right, C, CA. So here n are equal to 1, so it's the first order. Now check CA naught equal to 50 mole per meter cube, right. Now put this value in this equations. In this rate equal to twice this plus 0.1 CA over 1 plus 50 CA equal to 2 into 50 square plus 0.1 into 50 plus 1 plus 50 into 50. It 2 mole meter cube into time. Now uh, check this value for these equations. Rate 2 into T square divided by 50 into 50, right, it's a 2 mole per meter cube. But there here rate almost same, so it's a first order. Uh, so question 10 is the following liquid phase zero order reaction is carried out in constant volume isothermal batch reactor. A plus B gives R plus S. The reactant A and B as well as the product S are non-volatile gas. As the operating temperature, the saturation pressure of product H. Initially, the batch reactor contains equimolar amount of A and B. Is equimolar and no products. At a total pressure P 100 kilopascal. The initial concentration of reactants A naught and B naught equal to 12.5 mole per meter cube. The rate of reaction is given by minus RE is equal to 0.08 CA/CB mole per meter cube per second. The time at which R just start condensing rounded to the one decimal. So you have to calculate time just to start at a condensing. So here read given RA equal to 0.08 CA/CB. Right. Here mentioned that the equilibrium amount, so 0.08 CA square, right? Now for second order, Here some missing. Yes, is reaction. Not order. Right. The second order at a constant volume batch reactor, the rate equations xa is equal to 1 minus xa equal to a a naught to t. Right. Equation 1. Here given the 40 kilopascals PR 40 kilopascals. So here it is xa. So here is a partial pressure into xa into 40 kilopascal. Right. So here equal to zero point 0.5 mole fractions PTO. Right. Is equal to 0.5 into total pressure on 100 pascal equal to 50 kilopascal. The partial pressure is 50 kilopascal. Right. Now put a in this above equation. This one. So 50 to xa equal to 40. So xa is equal to 0.8. Right. Now here initial CA not given 12.5. Right. So put the value in this equation and calculate the time. So 0.8 to 0.2 equals to 0. Equal to 0.8 into 12.5 into t. Right. So t is equal to 4 seconds. Question number 11. For a gaseous reaction to twice A gives B, where the feed consists of 50% mole percent of A and 50 mole percent of inert. The expansion factor is. So to calculate the expansion factors is denoted by equal to V x equal to 1 minus V x is equal to 0 divided by x a equal to 0. So before conversion and after conversion. So here mole percent given are ideal gas volume percent equal to mole percent. Right. Now we see in feed 100 mole feed. Right. So here species initial and now. Right. A, B and here is a inert. So is a 50 inert is a 50. This is total. 100. So here final A is 0, B is 0.25, sorry, 25, it is the stuck, and inert will be the same, minimum products, which are total 75. Right. Now put it this equation 1, 75, and then minus 0.25. Option is now move to the question number 12. The first order gas phase reaction, the 2 gives to a phase B is conducted isothermally batch mode. The rate of change of conversion with time is given. There is a expansion factor twice as well. Right. So 1. So first order RA is equal to A1 CA. So A1 CA equal to 1 by V D A, sorry, divided by dt. So why we can write down or change in value 1 plus EMA not equal to D equal to minus XA by dt. Right. The concentration. So A naught was here, put the value factor XA into dx by dt. Right. So as we know, CA equal to CA naught equal to 1 minus XA 1 plus constant factor XA. Right. So equation. Right. Now, so put this value CA. Take this value CA. Right. Put this value CA is equal to in these equations. CA naught 1 plus XA equal to dxa by dt equal to A1 as naught 1 minus XA by 1 plus XA. Right. Therefore, dxa by dt equal to A1 1 minus XA. Now check the option is right. So I cover all the question based on the chapter course. If you have any doubt, please ask.